Hey everybody, so obviously I am not here today. I am at home because I am very sick and the world is spinning around. So that's fun for me. Oh, I don't know if you can hear this. My dog is here right now. Can you hear his breathing? That'd be really funny. Sorry, anyway. So this is the last thing that we're gonna learn for this unit. It is the two body problems. So these are the kinds of questions where we have more than one object. So the steps are going to be pretty similar. You're still going to be drawing your free body diagrams for both of the objects this time. That's really important. And then we're doing the Newton's second law, winners minus losers. And you'll be writing and solving the systems of equations like we were before. One thing that's really key about these kinds of questions is that when there's a string, the force of tension is going to be the same everywhere. So when there's a string or a rope, the force of tension will be the same for both objects. So this is kind of tying into what we talked about with Newton's third law, where well, on Friday, we had the example where Anag and I were pulling on the rope together. So if we were the two objects, we had the one force of tension between us, and that force of tension was the same for both Anag and I. So that's going to be really key when we're solving these questions. So let's start with step one on this example here. Two boxes are attached to a frictionless pulley, and that's really important because that's our key that says the force of tension is the same for both. So it's attached over a frictionless pulley, and we want to figure out what is the acceleration of the entire system, so of both of those blocks together. The key for this is that since both of these objects are attached, the acceleration will be the same. Right? If they're attached by a rope, one can't be accelerating more than the other. So then let's go ahead and let's try with the free body diagrams for each one first. So let's draw one for the 3 kilogram object and for the 5 kilogram object. When I look at this, immediately I know that it's going to be accelerating this way and this way because this 5 kilogram object is heavier, right? So I know that if I let this thing go, that one's going to win and it's going to pull it down and pull the 3 kilogram weight up. So when I'm drawing this in, then I'm going to say my force of gravity for the 5 kilogram block is going to be bigger than its force of tension, right? Because I know it should accelerate down. But then for the 3 kilogram block, we're going to have its force of tension be bigger than its force of gravity because I know that this one should be accelerating up. So I'm just going to draw a 5 and a 3 so that I know which one is which. But the nice thing is, again, these force of tensions are going to be the same. So now that I have my diagrams, let's write out the Newton's second law equation for each. We're going to get the force of gravity for the 5 kilogram block minus the force of tension is equal to the mass of the 5 kilogram block times the acceleration. And then over here, we're going to get the force of tension minus the force of gravity for the 3 kilogram block is equal to the mass of that 3 kilogram block times the acceleration. I'm going to rewrite them a little bit because I can rewrite force of gravity as Fg equals mg, right? So that's going to make it easier. So let me rewrite both of those next to each other over here. So instead of this, we're going to say 5 times g minus the force of tension equals 5 times a, because I'm plugging in those masses. And then for the other one, we're going to say force of tension minus 3g, because that's its mass, is equal to 3a. And so this is why I think it's really important when you're writing out your equations to keep in specifically which mass it is, because as you can tell, we're going to get a bunch of M's and A's and FG's and FT's in here, and it's going to get really easy to mix those up if you don't set it up nicely. Okay, so now when I have this, I know what G is, that's 10. I'm looking for A, and I don't know tension. So since I have two unknowns and two equations, I want to plug one into the other. So it's going to be helpful is that I can solve this system of equations by plugging in the force of tension here. So let me go ahead and just rewrite this one really quickly. When I add it to the other side, force of tension is equal to 3A plus 3G. Right, so that's what I'm going to plug in. So then when I plug in this system of equations, I'm going to get 5G minus, not force of tension, but 3A plus 3G is equal to 5A. And now it's just some algebra. Now I can plug in the force of gravity, or not the force, the acceleration of gravity being equal to 10, because that's going to make this a lot easier. And so then this equation is going to turn out to 50 minus 3A minus 30, because that negative sign gets distributed to each one, right, is equal to 5A. So then I can add my 3A to the other side, combine my 50 and my 30, so we get 20 is equal to 8A. And when I divide both sides by 8, 20 divided by 8 is going to get me an acceleration of 2.5 meters per second squared. And that's going to be the acceleration of both of the blocks because they're attached together. So this is still just a forces question, except now we're setting up an equation for both of these and we're plugging it in.